Look at a mechanical maze. To solve it rapidly, an object has to navigate dead ends, loopbacks, and sudden walls, constantly recalculating its physical trajectory to find the exit. In the literature of artificial intelligence, we test systems against problems like Sudoku, the shortest route in a traveling salesman scenario, or the exact placement of pieces in an n-queen chess problem. To human players, these look like entirely distinct challenges requiring separate, specialized strategies. To an AI system, their structures are identical. Solving any of these problems computationally relies on a single underlying algorithm. In AI, the process of finding the right sequence of actions is simply called searching. Watch this diagram. The chessboard, the geographic map, and the grid all map perfectly onto the same abstract structure, a uniform graph of interconnected nodes and edges. Engineers do not teach computers intuition. They strip away the human context entirely, reducing the puzzle to a formal environment where a computer can mathematically traverse those nodes. When a person plays Sudoku, they use intuition, glancing across the grid to spot missing numbers and make deductive leaps. A machine cannot glance. To make that puzzle computable, the rules have to be extracted and formalized into a strict methodology. This flowchart outlines that methodology. It is a 5-step problem-solving pipeline. Define the problem, analyze it, identify solutions, choose the best path, and implement the result. This pipeline serves as a mandatory bridge. It takes the abstract rules of a human game and translates them into a rigid architecture that a machine can actually search. Mastering these 5 specific steps is the foundational prerequisite for building any functional AI search system. We can see this pipeline in action using a classic pedagogical example, the 8 puzzle. The process starts with step 1, defining the problem. This step requires setting mathematical parameters. On the right, you see the puzzle's initial state. It consists of numbers 1 through 8 randomly distributed, leaving 1 blank space. Every coordinate is recorded to establish its starting position. Now look at the goal state next to it. The numbers are ordered sequentially, providing the strict coordinate the system must reach. The mathematical delta between this scrambled initial state and ordered goal state represents the specific problem area. Without establishing these exact starting and ending coordinates, an AI search algorithm cannot even initialize. It is completely blind. Once the coordinates are set, we move to step 2, analyzing the problem. Analysis means mapping out the rules of the environment. The algorithm needs to know exactly what movements are permitted within the defined problem area. This diagram shows the primary constraint of the 8 puzzle. Directional arrows indicate the AI can only slide tiles directly adjacent to the blank space. Any move jumping a tile or shifting diagonally is mechanically rejected. This limits the branching factor, the total possible future states. If these features are improperly analyzed or coded, the AI will generate physically impossible solution paths. These constraints define the geometric architecture of the entire search space. With the boundaries drawn, the system enters step 3, identifying solutions, which it accomplishes by generating potential paths forward. Look at the visual branching extending downward. The AI applies the constraints we just mapped to generate every immediate legal move from the starting block. These new matrices form the first layer of our search tree. This immediate expansion triggers step 4, choosing the best solution. The AI evaluates these newly generated states mathematically. The system continues to generate moves, dropping down into the next iteration, calculating the next set of valid tile positions. Then it expands again. The search tree grows exponentially, creating hundreds of potential grid configurations. The algorithm compares these branches, calculating which specific sequence of moves statistically brings the matrix closer to the goal state. Unhelpful branches that move tiles out of alignment are pruned from the system, isolating the single most efficient sequence of moves. In AI, iterations are never random guesses. They are the systematic mapping, expansion, and mathematical evaluation of a search tree. That careful evaluation sets up step 5, implementing the solution. Implementation is the final execution of the optimal path the algorithm just verified. Notice the brightly highlighted line. It traces a continuous, unbroken route from the initial state down through the correct iterations, directly to the goal state. The faded iterations surrounding it represent paths that were fully calculated but ultimately rejected. That finalized sequence of moves is now extracted. It is ready to be fed into an execution engine, like a robotic arm, to physically solve the puzzle. Implementation in artificial intelligence is merely the mechanical realization of the logical path already forged during the unseen, computational search phase. Stepping back from the 8 puzzle reveals a crucial operational reality about the broader landscape of artificial intelligence. Consider those varied problems we started with: measuring out liquid in the water jug problem, navigating a chessboard, or stacking rings in the towers of Hanoi. Our 5-step flowchart maps perfectly onto these wildly different challenges. The water jug problem requires the identical mathematical definition of starting and target volumes. Chess requires mapping piece constraints to limit search space growth. NenQueen builds the exact same multi-layered search tree. The physical, human-facing nature of the puzzle, whether it uses numbers, water, or wooden pieces, is completely irrelevant to the underlying architecture. AI problem-solving centers on the formal definition of a state space and the systematic search for a verified solution.